All right, so last few days we've been doing just a lot of kind of going over Newton's second law, looking at problems, solving problems. I figured we'd break it up a little bit and do our lab on Newton today, since we talked about pulleys and systems the last couple of days, so we should be able to handle what's going to happen in this lab. All right, so what we're doing is we're trying to essentially validate or verify Newton's second law. Right? The way we're going to do that is we're going to use the carts, okay, that we've used before. And what we're going to do is we're going to tow them using a mass that's going to fall. So we're just going to rig this up so that our carts are tied to the string, and then tied to the other end of the string over the pulley will be some hanging mass. So we're going to use the force of gravity as our towing force. Okay, everybody with me so far? That's not too tough. Okay, so we're going to have this towing force, okay, that's going to pull the cart along. And all we're going to do is continually change the amount of mass hanging over the pulley so that we can change the amount of applied force, okay, or towing force. Everyone follow there. All right, so every single time we do a trial, we're going to change the amount of applied force that is going to be used in the lab. Each time, we are going to measure the acceleration of the cart. We're going to do that using a velocity versus time graph. Okay, so you're going to have a velocity versus time graph that's got all of your trials on it, and then obviously the slope of the line on that graph will be your acceleration for each trial, and we'll be able to measure whether the increased applied force is causing a change, a linear change, hopefully, okay, in the acceleration of the cart. Now, our results here should be fairly obvious. It wouldn't be Newton's second law if it hadn't been confirmed time and time again for the last several hundred years. Okay, so we're pretty sure this is going to work. And by pretty sure, I mean if it doesn't, you did something wrong because physics did something right. Okay? Okay. All right. So the setup, like I say, will be that we'll have the cart attached to the string, okay, and we'll have the hanging masses hanging over the pulley. Now, something that has to stay the same throughout this entire lab, and it's crucial, is the mass of the system. That can't change. We want to be accelerating the same amount of mass each time because we know mass also affects acceleration. We only want to test the effect of the applied force on the system, not the mass. So I can't just add mass over the pulley each time. I have to keep the mass of the system, that's the mass over the pulley and the cart, the same, while continuing to change the amount of mass that's over the pulley. How am I going to do that? Exactly. I'm going to start with mass on top of the cart as well. I'm just going to transfer the mass from the top of the cart over the pulley. That way the mass of the system stays the same, and I know now that I've controlled the other thing that can affect acceleration. Okay? Okay, if you were really paying close attention, you just got 3 out of the 5 variables in the last minute and a half. Okay? All right. So that's how this is going to work. And like I said, we're just going to transfer mass over the pulley each time. Okay? Hopefully gravity's not going to change too much also during the lab. Okay. So for our hypothesis, okay, because now we've kind of gone over the design here, okay. For the hypothesis, we got our if, and then statements, okay. The if part should talk about what is Newton's second law, okay. That's the if part. What is Newton's second law? Okay, so basically the if part for you needs to say something about how force and acceleration are related. Okay, that's the if part, that's what we're testing. Okay, the and part just describes the experiment. Okay, a system with a set mass is going to have varied forces applied to it with the accelerations being measured. Okay, something along those lines. Okay, and then the then part needs to predict your results. Okay, so as applied force increases, acceleration will whatever. Okay, that's your then part. questions so far? So our procedure is going to go as follows, okay? Sorry, the cart's mass is not 502. That was our old masses. We have the mass of the carts written on blue tape on each cart, okay? For some reason, the red ones have a different mass than the blue ones, but the blue ones are all the same, the red ones are all the same. I don't know.
They're like different models? Or?
No, they're exactly the same. The red plastic is heavier, I think heavier by like 2 grams. I don't know. Okay, well, we did measure them all, but then maybe the dye is heavier. But they're different, and Mr. Dickey and I measured both. So, yeah, the mass is on there, and then of course you'll also have to add on to that whatever mass is hanging or is placed on the cart. Now, a key thing here, because we have to avoid Newton's first law, making fools of us during this lab. So we have this high-tech material, sticky tack, okay, that will be used to hold the masses in place on the cart. Because if you just have this thing sitting on the track and then you let go of the masses and it starts to move, the inertia of the masses on the cart say that they'll stay put, and the cart just slides right out from underneath them, okay, just like the tablecloth from under the dishes. So we don't want that, okay. Put a little tiny bit of sticky tack on the bottom of the masses that are sitting on here, and they'll stay put enough for our lab, okay. All right. So we're going to start out with with this setup. You need to make sure your masses are as far above the floor as possible given your setup. So about 90 centimeters or so. Okay, so have them right at the bottom of the pulley. Okay, someone is going to hold the cart. That way there's tension in the string when you start. Okay, because some groups, they hold the mass and then the string goes slack. And then the masses fall and then they pull on the string and there's this massive jerk right away. It doesn't look good in the data. Okay, so you want to be holding the cart. Okay, release the cart when your timer person says to do so. Okay? And for this one, guys, you gotta kind of make sure that the timer is already running when the person releases it. So you as the person with the phone, okay, watch it when you start seeing stuff come on there, then tell them to let it go. You can always edit out those dots that happen before they let it go, because this happens fast, especially when you've got lots of mass hanging over the pulley. Okay, the first trial is pretty slow, but after that they go faster and faster. Okay, so this is the chart you're going to have to fill in. Okay, so you're just going to put in your hanging masses, mass of the cart and the masses. Okay, your acceleration, which you'll get from the slope of the velocity time graph. Your net force, that'll be the mass of the system times the acceleration, okay, which you will have. And then your applied force, okay, is going to be the hanging masses times 9.81. What is the theoretical relationship between these two forces for this lab? Okay, so I've got the cart sitting on the ramp. I have this force over here. When I let this go, this force pulls the cart. Theoretically, that force and the net force should be
the same.
Yeah. Okay, they should be the same, theoretically. Now, are they going to be exactly the same? Because there's probably some other forces that are going to come into play. That's something you need to watch for, okay, in the lab. And one of the things you need to watch for when you set this up is that this is level, right? You can use your phone to tell, okay? Your phone has a level, it's in the measure app. Okay, if you have an iPhone, just open up the measurement app and it says measure and then level. Okay, just click level and set your phone on there. Okay, make sure it's within, like it's on 0, hopefully, okay, this way. I'm not too worried about whether it's level this way, it should be pretty close. It's the way the cart is going, that way needs to be level. So if you've got to, stick something underneath or whatever to make it level, you got to do that, okay? Because if you don't make it level, are you bringing in some other forces? Okay, and there's probably another force that may be present here since we have surfaces moving past each other. Okay, all right. Theoretically, they should be pretty close. All right. So when we're doing this, okay, like I said, we got the mass of the cart, okay, plus whatever mass we have hanging over, okay, and these are the masses that you're going to use to drive the system, okay. So on the first trial, you're going to have 50 grams hanging over the pulley, okay, and and you're going to have 400 grams on the cart. Okay, everybody got that? So first trial, you're going to have 50 grams hanging over the pulley, and you're going to put 400 grams on the cart. Okay. In your next trial, you're going to take 50 grams off the cart and add it to the mass over the pulley. Each time we do this, you're taking 50 grams off the cart and putting it over the pulley. Now, there are not that many 50-gram masses. So you got to do a little permutations and combinations kind of thing here, okay, in order to always get the right mass, okay, hanging over the pulley. Okay, and the way you can do that, guys, when you're adding mass over the pulley, the bottoms of the masses have a little bar on the bottom. Okay, so you can do that. Right? You can hang them off of each other, okay, when you're adding mass over the pulley. Now, the first time, maybe you have a 50-gram mass hanging over the pulley. Okay, on your second trial, you take it off, you take the 100-gram mass off the cart, you hang it over the pulley, you put the 50-gram mass back on the cart. You've just transferred 50 grams off the cart and over the pulley. Okay, that's that whole permutations, combinations thing you're going to have to do. All right. Okay. So those are the trials you're going to do. 4 trials. Okay, you're going to have 4 trials. You're going to get the acceleration data, okay, for each one, and then you're going to build in Google Sheets a velocity versus time graph that has 4 sets on it. Okay, put a best fit line on for all 4. Okay, the slope of that line is your acceleration for each one of the trials. That's going in this row right here. Okay, and you'll need that obviously because we're going to be going mass times acceleration to see what the net force is. Okay. So hopefully you're going to get something that looks, well, obviously the graphs look different. Okay, but it's going to have this pattern: slower, faster, faster, fastest. Okay, and that's what we should see. Okay. Now, for your analysis, okay, you're going to apply a linear fit. Obviously, we already talked about that's building the graph. Okay, calculate the applied force value, put that in the chart, so we'll have already done that. Okay, calculate the force acting on the cart. Okay, that's your mass times. What's the relationship between net force and the acceleration of the cart? So look at that as the net force increases, what was happening to the acceleration. Okay, number 5, this is an important one. Okay, draw a free body diagram to describe the forces involved on the cart and the hanging masses. Okay, so I'm going to want to see a free body diagram. Okay, you can draw that on paper, take a picture of it, and insert that picture right here in the Google Doc. All right, so you'll have your desk, you got your pulley, okay, and you're going to have, there's your hanging masses, okay, here's your cart. Obviously, each trial, the numbers are different. I'm not looking for you to put numbers in the boxes. I'm just looking for you to identify forces that may or may not have been present, okay, in your experiment. Okay, at this point, you'll have already compared the net force and the applied force. If they're not equal, you've got to figure out what forces were going on here. Okay, and that means you really have to look at your data. If your net force is less than the applied force, was there a helping or a hindering force? Right. Okay. If your net force is greater than your applied force, then there was a helping force. You got to figure out what those were. Okay. Those go on the free body diagram. And then number 6, explain. Okay. Why did that happen? Okay. Why did you get the results you did? Okay. Then you got your conclusion. Copy paste your hypothesis, same as always, and then look for sources of error. This is a good place to look for your sources of error, because we probably didn't account for all the other forces that would have been involved in the experiment. Okay? All right. Questions on what we're doing?
Do you want all of the lines of acceleration on one graph?
Yes. Please put them all on one graph. Okay. Any other questions? All right. Have at it. Okay, somebody can use the setup there if they want. Okay, I'm going to put the sticky tack over here with the masses. Okay, make sure everybody stays matched up while we're doing this. You do have to do this on, last thing. In your group, one person's job is to stop the cart. Okay, don't watch the cart. If you watch the cart, it's going to hit this and it's going to launch. It's going to take out the pulley, and then the cart's going to break too. Okay, and these are good pulleys. Okay, They're very minimal friction. They spin for a really, really long time. Okay, so we don't want either the cart or the pulley to get wrecked. Okay, I do not want to be coming over to a group and going, "You had one job." Okay, because you had one job. Stop the cart. That's, you assign that to the most responsible person in the group, please. Okay, make sure they're on the ball. If you don't have a responsible person in your group, find one. Okay? All right, let's get to it.
All responsible.